Which of the following statements accurately describes the functionality of MaxABS scaler in scikit-learn? Scales each feature by dividing by its maximum absolute value. Scales each feature to a specified range, example 0 to 1. Scales each feature by subtracting the mean and dividing by the standard deviation. Scales each feature to have zero mean and unit variance. All of the above. This statement is correct. MaxABS scaler scales each feature by dividing its value by the maximum absolute value observed in that feature across the dataset. This ensures that all values in a feature are scaled to a range between -1 and 1. A scales each feature by dividing by its maximum absolute value. This statement is incorrect. MaxABS scaler does not scale features to a specific range. Instead, it scales them based on the maximum absolute value of each feature, resulting in a range between -1 and 1. B scales each feature to a specified range, example 0 to 1. This statement is incorrect. Scaling by subtracting the mean and dividing by the standard deviation is the functionality of standard scaler, not MaxABS scaler. C scales each feature by subtracting the mean and dividing by the standard deviation. This statement is incorrect. Scaling features to have zero mean and unit variance is the functionality of standard scaler, not MaxABS scaler. D scales each feature to have zero mean and unit variance. This statement is incorrect. Only choice A is correct. MaxABS scaler does not scale features to a specific range, nor does it subtract the mean and divide by the standard deviation. E. All of the above. A. MaxABS scaler is a feature scaling technique in scikit-learn that scales each feature by dividing its values by the maximum absolute value of that feature across the dataset. This method ensures that all values in a feature are scaled to a range between -1 and 1. Data with large feature ranges. When dealing with datasets where features have vastly different ranges, example 1 feature ranges from 0 to 100, while another ranges from 0 to 1000, MaxABS scaler can help normalize the data. This prevents features with larger ranges from disproportionately influencing machine learning models. Sparse data. MaxABS scaler is particularly suitable for sparse data. Sparse data contains many zero values, and calculating the mean or standard deviation for such data can be computationally expensive. MaxABS scaler avoids these computations, making it efficient for sparse data sets. Preserving sparsity. MaxABS scaler helps preserve the sparsity of the original data. This is important for algorithms that perform well with sparse data representations, like certain recommendation systems or text processing models. From sklearn.preprocessing import MaxABS scaler. Scaler MaxABS scaler. Scaled data scaler.fitTransform data. This code snippet demonstrates how to use MaxABS scaler in Python. First, you import the MaxABS scaler class from scikit-learn. Then, you create an instance of MaxABS scaler. Finally, you use the fitTransform method to scale your data. The fitTransform method first learns the maximum absolute value of each feature from the data and then applies the scaling transformation. 10, 20, 5, 15, 25, 5, 0.4, 1.0, 0.2, 0.75. 1.0, 0.25. In this example, the maximum absolute values for the first and second features are 25 and 20, respectively. MaxABS scalar divides each value by its corresponding maximum absolute value, resulting in the scaled data shown above. Feature scaling. The process of transforming features to a common scale. This can be necessary for algorithms that are sensitive to feature ranges, such as distance-based algorithms like k-nearest neighbors or algorithms that use gradient descent. Normalization. Scaling features to a specific range, often between 0 and 1. Normalization is particularly useful for algorithms that rely on distances or probabilities. Standardization. Scaling features to have zero mean and unit variance. This is often used to make features have similar distributions and to improve the performance of algorithms like linear regression or support vector machines. Robust scalar. Similar to MaxABS scalar, but instead of using the maximum absolute value, it uses percentiles, typically the 25th and 75th percentiles, to determine the scaling factor. This makes it more robust to outliers. Min-max scalar. Scales features to a specific range, example 0 to 1, by subtracting the minimum value and dividing by the range of the feature. This is commonly used for image processing or when you need to guarantee that all features are in a specific range. Standard scalar. Scales features to have zero mean and unit variance by subtracting the mean and dividing by the standard deviation. This is often used for algorithms like principal component analysis (PCA) or linear regression. What is the primary function of min-max scalar in scikit-learn for pre-processing numerical data? A. Standardize features to have zero mean and unit variance. B. Transform features to a specified range, usually 0, 1. C. Encode categorical features into numerical values. D. All of the above. False. This is the function of standard scalar, not min-max scalar. Standard scalar transforms features to have zero mean and unit variance. The formula is scaled x, smean x std. True. This is the primary function of min-max scalar. It scales features to a specified range, typically 0, 1, using the formulas scaled x, smin smax, smin. False. This is the function of encoding techniques like one-hot encoding or label encoding. Min-max scalar focuses on scaling numerical features, not encoding categorical ones. False. While min-max scalar is a pre-processing technique, it does not encompass all the pre-processing tasks listed. Standardization A is handled by standard scalar, and categorical encoding C is addressed by specific encoding methods. B. Preparing data for machine learning models. Includes tasks like scaling, encoding, and handling missing values. Imagine building a model to predict house prices based on factors like area, number of bedrooms, and location. Before feeding this data to the model, pre-processing steps like scaling numerical features area and encoding categorical features location are crucial. Transforming features to have a similar scale, preventing features with larger magnitudes from dominating the learning process. In a model predicting customer churn, features like average transaction amount might have a much larger scale than number of complaints. Scaling ensures that these features contribute fairly to the model's predictions. Scales features to a specific range, typically 0, 1, by adjusting values based on the minimum and maximum values in each feature. When building a model to classify images based on pixel values, min-max scaler can be used to scale each pixel value to the range 0, 1, ensuring that no single pixel dominates the model's decision. Transforms features to have zero mean and unit variance using the following formulas: scaled x, smean x std. In a model predicting customer satisfaction scores, standardization can help normalize the scores across different demographics, ensuring that the model is not biased towards one particular group. Distance-based algorithm scaling prevents features with larger magnitudes from disproportionately influencing distance calculations. In a recommendation system using KNN to suggest similar products, scaling ensures that a product's price does not unduly influence the similarity score compared to other features like customer ratings or product descriptions. Margin-based algorithm scaling helps in finding the optimal hyperplane by avoiding bias towards features with larger scales. When training an SVM to classify customer sentiment based on text data, scaling ensures that words with higher frequencies do not dominate the decision boundary, leading to a more accurate classification. Gradient-based algorithm scaling improves the convergence of the optimization process by preventing gradients from being dominated by features with larger scales. When training a neural network to predict stock prices, scaling ensures that the network learns effectively from both price and volume data, preventing the network from being overly influenced by price fluctuations. Which of the following statements correctly describes the sklearn normalizer's purpose? Scales features to a specific range, typically between 0 and 1. Transforms features by removing the mean and scaling to unit variance. Rescales features to have unit norm length 1. All of the above. Rescales features to have unit norm length 1. This statement describes min-max scaling, not normalization. Min-max scaling scales features to a specific range, typically between 0 and 1. Feature scaling. This statement describes standardization, not normalization. Standardization transforms features by removing the mean and scaling to unit variance. Feature scaling. This is the correct description of the sklearn normalizer. It rescales each sample row to have a unit norm length 1 using the Euclidean norm. This ensures that all samples have the same length, making it useful for algorithms that rely on the magnitude of features. Euclidean norm. This statement is incorrect because only option C is the correct description of the sklearn normalizer. None. Feature scaling. Preparing data for machine learning algorithms by adjusting the scale of features. Different algorithms are sensitive to feature scales. This often involves techniques like normalization, standardization, or min-max scaling. In a recommendation system where user preferences are represented by features, scaling these features using techniques like normalization can help improve the accuracy of recommendations by ensuring that all features contribute equally to the similarity calculations. Euclidean norm. The length of a vector calculated using the Pythagorean theorem sum of squared elements. The normalizer scales each sample to have a Euclidean norm of 1. Consider a dataset with features representing the distance traveled by different vehicles. Normalizing these features using the Euclidean norm would ensure that all vehicles are treated equally regardless of the total distance traveled, allowing for better comparisons based on relative distances. Cosine similarity. A measure of similarity between two vectors based on the angle between them. It's not affected by the magnitude of the vectors, making it useful when the direction of the features is more important than their scale. In a document similarity search engine, normalizing document vectors using the normalizer can improve the accuracy of searches by ensuring that the cosine similarity between documents is not influenced by the length of the documents. Recommender systems when calculating user item similarity using cosine similarity, normalizing the vectors can improve the accuracy of recommendations. Consider a movie recommendation system where users rate movies. Normalizing user ratings using the normalizer can ensure that recommendations are not skewed towards users who have rated a large number of movies. This can help in recommending more accurate and relevant movies based on user preferences. Text classification normalization can help in text classification tasks where document vectors have varying lengths. It can improve the performance of algorithms like k-nearest neighbors KNN. In a spam detection system, normalizing document vectors representing emails can ensure that the classification algorithm is not biased towards longer emails. This can help in identifying spam emails more effectively. Image recognition in image classification tasks, normalizing pixel values can enhance the performance of neural networks by preventing them from being influenced by large pixel values. In a face recognition system, normalizing the pixel values of images can help the neural network focus on the important features of the face, such as eyes, nose, and mouth, regardless of the overall brightness or contrast of the image. Collaborative filtering normalization helps in collaborative filtering algorithms when measuring the similarity between users or items based on their preferences. In a music recommendation system, normalizing user listening histories can ensure that recommendations are not biased towards users who have listened to a large number of songs. This can help in recommending more accurate and relevant songs based on user preferences. From sklearn. Preprocessing import normalizer. Data 1, 2, 3, 4, 5, 6. Normalizer. Normalized data normalizer. Fit transform data. Print normalize data. This code snippet demonstrates the use of the sklearn normalizer. It first creates a normalizer object. Then, it applies the fit transform method to the input data, which both fits the normalizer to the data and transforms the data to have unit norm. Finally, the normalized data is printed. Which of the following statements are true regarding one-hot encoder in scikit-learn? A. It converts categorical features into numerical ones by creating binary columns. B. It handles both nominal and ordinal categorical features. C. It can be used to create sparse matrices for memory efficiency when dealing with high cardinality categorical features. D. All of the above. This statement is true. One-hot encoder converts categorical features into numerical features by creating binary columns 0s and 1s for each unique category. This allows machine learning algorithms to understand and process categorical data. True. This statement is true. One-hot encoder can handle both nominal unordered and ordinal ordered categorical features. It treats each category as a separate feature, regardless of its ordering. True. This statement is true. When dealing with high cardinality categorical features, many unique categories, one-hot encoder can result in a large number of columns. To address this, it can create sparse matrices, which only store the non-zero values, leading to memory efficiency. True. This statement is true. All the previous statements about one-hot encoder are correct. True. D. All of the above. A technique used in machine learning to convert categorical features into numerical features by creating binary columns for each unique category. Features that represent categories or labels instead of numerical values. Example color can be red, blue, green. Categorical features where the order of categories doesn't hold any significance. Example color red, blue, green, no specific order. Categorical features where the order of categories holds significance. Example size small, medium, large, has a specific order. Matrices where most of the elements are zero. They efficiently store data by only storing non-zero elements. This helps conserve memory when dealing with high-dimensional data, such as one-hot encoded features with high cardinality. Many machine learning algorithms, like linear regression, logistic regression, and support vector machines, require numerical data as input. Data with many distinct categories in a particular feature. Example: a dataset of customer purchases with a product feature that has 1000 unique products. Red. Small. 10. Blue. Medium. 15. Green. Large. 20. 1. 0. 0. 1. 0. 0. 10. 0. 1. 0. 0. 1. 0. 15. 0. 0. 1. 0. 0. 1. 20. Predicting customer churn based on demographics and purchase history. Classifying images of different objects in a dataset. What is ordinal encoder in sklearn? A. It encodes categorical features into numerical features by mapping each unique category to a unique integer value. B. It encodes categorical features into numerical features by mapping each category to a numerical value based on its frequency. C. It encodes categorical features into numerical features by mapping each category to a numerical value based on its alphabetical order. D. All of the above. Correct. The ordinal encoder can assign a unique integer to each distinct category. For example, if you have categories like small, medium, and large, it could assign 0 to small, 1 to medium, and 2 to large. This method preserves the order between categories, making it suitable for data with inherent ordering. Correct. The ordinal encoder also allows mapping categories to numerical values based on their frequency in the dataset. This can be useful for capturing the relative importance of different categories. For instance, if large appears more frequently than small, it could be assigned a higher numerical value. This approach preserves the order of categories based on their frequency. Correct. The ordinal encoder can encode categories alphabetically. This means the categories are ordered based on their alphabetical order, and the numerical values are assigned accordingly. For example, if the categories are large, medium, and small, it would assign 0 to large, 1 to medium, and 2 to small. This method can be helpful when the categories have a natural alphabetical order. Correct. This choice is correct because the ordinal encoder in scikit-learn provides all the mentioned encoding strategies. It allows you to choose the most appropriate strategy based on your data and the desired outcome. D. All of the above. Categorical features. These are features representing discrete categories. They are often represented as text values but need to be transformed into numerical data for use in machine learning models. Examples include color, gender, product type, and city. In a customer data set, the gender feature would be a categorical feature with values like male and female. Numerical features. These features represent continuous or discrete numerical values. They are readily usable by most machine learning models. Examples include age, income, number of products purchased, and temperature. In a sales data set, the quantity ordered feature would be a numerical feature, as it represents the number of products ordered by a customer. Machine learning models. These are algorithms designed to learn patterns from data. They use numerical data to make predictions or classifications. Examples include linear regression, decision trees, support vector machines, and neural networks. A linear regression model can be used to predict the price of a house based on its size, location, and number of bedrooms. Data preprocessing. This involves transforming raw data into a format suitable for machine learning models. It often includes steps like cleaning, transforming, and encoding data. Ordinal encoding is a data preprocessing technique used to convert categorical features into numerical features. Before training a machine learning model on customer data, you might need to preprocess the data by encoding categorical features like marital status and occupation into numerical values. Feature engineering. This involves creating new features from existing ones to improve the performance of machine learning models. It can involve combining, transforming, or creating entirely new features. You could engineer a new feature called age group by grouping customer ages into categories like young, middle-aged, and senior. This could improve the accuracy of a model predicting customer purchase behavior. Feature engineering. Ordinal encoding transforms categorical features into numerical features, making them compatible with most machine learning algorithms. This is a crucial step in preparing data for training machine learning models. Imagine you have a data set of customer data, including education level as a categorical feature with values like high school, bachelor's, and master's. Ordinal encoding can transform these values into numbers, allowing you to use them in a machine learning model to predict, for example, customer spending patterns. Data preprocessing. Ordinal encoding is an essential part of data preprocessing. It ensures that data is in a format suitable for machine learning algorithms, which often require numerical inputs. Before training a model to predict loan approval rates, you might need to encode categorical features like credit score categorized as excellent, good, fair, and poor using ordinal encoding to represent them numerically. This prepares the data for the model, which can then make predictions based on the encoded numerical values. Handling ordinal data. When dealing with ordinal data where order matters, ordinal encoding can be used to preserve the relationship between categories. This ensures that the encoded numerical values accurately reflect the order. If you have a data set of product reviews, where rating is an ordinal feature with values like 1 star, 2 stars, 3 stars, 4 stars, and 5 stars, ordinal encoding can effectively represent this order numerically. This allows you to use the rating in a machine learning model to predict, for instance, customer satisfaction. Which of the following statements are true about sklearn. Preprocessing. Polynomial features. A. It generates polynomial features from existing features. B. It can be used to add nonlinearity to a linear model. C. It can increase the complexity of a model. D. All of the above. D. All of the above. This is true because sklearn. Preprocessing. Polynomial features explicitly transforms existing features into polynomial features. For example, if a feature x is present, it generates features like x2, x3, and so on, depending on the degree parameters specified. Sklearn. Preprocessing. Polynomial features is a transformer that generates polynomial features from existing features. This is true because adding polynomial features allows a linear model to capture nonlinear relationships in the data. For instance, a linear model with an added quadratic term can fit a parabola, which is a nonlinear function. By adding polynomial terms to the features, we can fit nonlinear models, thus increasing the model's complexity. This is true because adding polynomial features increases the number of features and therefore the complexity of the model. A model with more features can potentially fit the training data better but may also be prone to overfitting. By adding polynomial terms to the features, we can fit nonlinear models, thus increasing the model's complexity. All the above statements are true, as explained for each option. Sklearn. Preprocessing. Polynomial features is a transformer that generates polynomial features from existing features. This is useful for capturing nonlinear relationships in data. By adding polynomial terms to the features, we can fit nonlinear models, thus increasing the model's complexity. Feature engineering. Feature engineering is the process of creating new features from existing ones. This often involves transforming raw features into forms more suitable for machine learning models. In a house price prediction problem, we can engineer features like area per bedroom or age of house from features like area, bedrooms, and built year. Polynomial regression. Polynomial regression is a type of regression analysis that uses polynomial functions to model the relationship between the independent and dependent variables. It is capable of capturing nonlinear relationships in the data. Imagine you have a dataset with the number of hours studied X and the corresponding exam scores Y. You can use polynomial regression to model the relationship between the two variables, potentially using a quadratic function to capture an initial increase in scores followed by a plateau as study time increases. Polynomial features is a key tool for polynomial regression as it provides the polynomial terms needed for fitting a polynomial model. Model complexity. Model complexity refers to the number of parameters or degrees of freedom in a model. A complex model can fit training data well but might overfit and perform poorly on unseen data. A linear regression model is less complex than a polynomial regression model with higher order terms. The linear model has fewer parameters to adjust, leading to a simpler model. Overfitting. Overfitting occurs when a model learns the training data too well, including noise and random fluctuations. This results in a model that performs poorly on unseen data. A model that overfits a dataset with noise might learn that a specific pattern of noise is correlated with the target variable, leading to poor predictions when encountering new data without that noise pattern. Regularization. Regularization is a technique used to prevent overfitting by penalizing complex models. It adds a penalty term to the loss function, discouraging the model from relying too heavily on individual features. Lasso regression is a type of linear regression that uses L1 regularization, which penalizes the sum of absolute values of the coefficients. This can effectively reduce the number of features used by the model, leading to a simpler and more robust model. Predicting house prices based on nonlinear relationships between features like area, bedrooms, and location. A linear model might not capture the complex relationship between house prices and factors like the number of bedrooms and the neighborhood's desirability. Polynomial features can help the model learn nonlinear patterns, resulting in more accurate predictions. Modeling customer behavior based on factors like purchase history, demographics, and browsing patterns. Customer behavior is often influenced by a combination of factors that interact in nonlinear ways. Polynomial features can help a model capture these complex interactions, leading to better predictions of customer purchasing decisions. Question: which of the following statements accurately describes the purpose of scikit-learn's power transformer? A scales features to a specified range, typically between 0 and 1. B transforms features to a normal distribution Gaussian. C reduces the influence of outliers by replacing them with the median. D all of the above. Incorrect. Power transformer does not focus on scaling features to a specific range. Scaling is typically achieved using techniques like min-max scaler or standard scaler. Correct. This is the core purpose of power transformer. It employs the Yeo-Johnson or Box-Cox transform to approximate a normal distribution for features. This transformation is crucial for algorithms that assume normally distributed data. Incorrect. While power transformer might indirectly handle outliers, its primary goal is not outlier replacement. Outlier handling is typically addressed using techniques like robust scaling or outlier removal. Incorrect. Only statement B is accurate. Statements A and C describe different preprocessing techniques. B. Preprocessing is the crucial step in preparing data for machine learning models. It involves transforming and cleaning data to improve the model's performance, accuracy, and robustness. Data transformation involves altering the representation of data without changing its inherent meaning. It aims to make data suitable for the specific machine learning model being used. Feature scaling involves adjusting the range of features to a common scale. This is particularly important for distance-based algorithms like k-nearest neighbors or support vector machines. Techniques like min-max scaler or standard scaler are commonly used. Outliers are data points that are significantly different from other data points. They can negatively impact model training. Techniques like outlier removal, replacing outliers with a fixed value, or robust scaling are often employed. Power transformation is a specific type of data transformation that aims to make data more normally distributed. It's valuable for algorithms that assume normally distributed data. Two commonly used methods are the Yeo-Johnson and Box-Cox transformations. The Yeo-Johnson transformation handles both positive and negative values, making it versatile for a wider range of data. It uses a power transformation to approximate normality. The Box-Cox transformation primarily works with positive data and applies a power transformation to make the data more symmetric and closer to a normal distribution. A normal distribution is a bell-shaped probability distribution. Many statistical models and machine learning algorithms assume that data is normally distributed. Power transformations can help bring data closer to this ideal distribution. Linear regression models often perform better when the features are approximately normally distributed. Applying power transformer to the data can help improve the model's predictions. Logistic regression, similar to linear regression, can benefit from normally distributed features. Power transformation helps make the data more suitable for the model. Support vector machines (SVMs) rely on the distance between data points, and normalizing features through power transformer can improve the separation of classes and enhance classification accuracy. Certain neural network architectures assume normally distributed inputs. Power transformation can help pre-process data to match these assumptions, potentially leading to better learning and performance. LTF style quad font family monospace font size 12 Scott from sklearn. Preprocessing import power transformer LTBRK from sklearn. Datasets import load Boston LTBRK Boston load Boston LTBRK text Boston. Data LTBRK power transformer method EO Johnson, standardized true LTBRK transformed PT fit transforms load dived. This code snippet demonstrates how to apply power transformer to a dataset using sklearn. It loads the Boston housing dataset, creates a power transformer object using the Yeo-Johnson method and standardization, and then transforms the data to approximate a normal distribution. The standardized true argument ensures that the transformed features have zero mean and unit variance, which can further improve the model's performance. Example: suppose we have a dataset with a feature income that is highly skewed. Applying power transformer using the Yeo-Johnson method can transform the data closer to a normal distribution. 10,000, 15,000, 20,000, 25,000, 30,000. 50,000, 100,000. The Yeo-Johnson transformation applies a power transform with a lambda parameter determined based on the data distribution. This helps to normalize the data and make it closer to a normal distribution. Which of the following statements accurately describes the sklearn quantile transformer? A. It transforms features to follow a uniform distribution. B. It scales features to a specific range, typically 0, 1. C. It replaces outliers with values closer to the median. D. It transforms features to follow a normal distribution. E. All of the above. Correct. The quantile transformer can transform features to follow a uniform distribution. This is achieved by mapping the quantiles of the original data to the corresponding quantiles of a uniform distribution. This can be useful when the original data is not evenly distributed and a uniform distribution is preferred for the modeling task. Imagine you have a dataset with income data that is heavily skewed towards lower income values. Transforming this data to follow a uniform distribution can help in making the model more robust to outliers and improving its performance. Let's say we have the following income data: 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. After applying quantile transformer, this data will be transformed to follow a uniform distribution, meaning the distribution of the transformed data will be equally spread across the entire range, unlike the original data, where the data was more concentrated towards the lower income values. Correct. The quantile transformer can scale features to a specific range, typically 0, 1. This is achieved by mapping the quantiles of the original data to the corresponding quantiles of a uniform distribution within the specified range. This scaling helps to normalize the data and can be beneficial for algorithms sensitive to feature scale. In a machine learning model where features have different scales, such as age and income, scaling them to a common range can improve the model's performance by preventing features with larger scales from dominating the model's learning process. Let's say we have two features, age and income. Age is typically in the range of 0 to 100, while income can be in the range of 1000 to 10,000. Applying quantile transformer with the range 0, 1 will scale both features to be within this range. This will make the model treat both features equally, regardless of their original scales. Correct. The quantile transformer can handle outliers by replacing them with values closer to the median. This is achieved by mapping the quantiles of the original data to the corresponding quantiles of a uniform distribution. Outliers, which are usually located at the extreme tails of the distribution, are then mapped to values closer to the median, reducing their impact on the model's learning process. In a dataset with age data where there might be a few very high ages due to errors in data entry, the quantile transformer can help to mitigate the effect of these outliers by mapping them to values closer to the median age, improving the model's accuracy. Let's say we have the following age data: 20, 25, 30, 35, 40, 45, 50, 100. The value 100 is an outlier in this dataset. Applying quantile transformer will map this value to a value closer to the median age 35, reducing its influence on the model's learning process. Correct. The quantile transformer can also transform features to follow a normal distribution. This is useful for algorithms that assume data to be normally distributed. By mapping the quantiles of the original data to the corresponding quantiles of a normal distribution, the data becomes more suitable for these algorithms. Linear regression, a commonly used algorithm, often performs better with data that follows a normal distribution. Applying quantile transformer to transform features to follow a normal distribution can improve the performance of linear regression models. Let's say we have a dataset with height data that is not normally distributed. Applying quantile transformer with the output distribution set to normal will transform the height data to follow a normal distribution, making it more suitable for algorithms like linear regression. Correct. All of the above statements are accurate descriptions of the sklearn quantile transformer. This makes it a highly versatile and powerful tool for pre-processing data in various machine learning tasks. The quantile transformer is a versatile tool that can be used in various machine learning applications, such as image recognition, natural language processing, and time series forecasting. It can be applied to handle outliers, normalize data, and transform data to specific distributions, all of which can improve the performance and accuracy of machine learning models. The versatility of quantile transformer is evident in its ability to transform data to various distributions, such as uniform, normal, or a specific range. This allows it to be used in a wide range of machine learning tasks, making it a valuable tool in the data scientist's toolkit. All of the above. Feature scaling, outlier handling, data transformation, image recognition, Natural language processing. Time series forecasting. Which of the following statements accurately describes the primary function of robust scaler in scikit-learn? A scales features to a specified range, typically between 0 and 1. B standardizes features by removing the mean and scaling to unit variance. C transforms features to have a median of 0 and a quantile range of 1, making it robust to outliers. A scales features to a specified range, typically between 0 and 1. This describes the function of min-max scaler, not robust scaler. Min-max scaler scales features to a specific range, example 0 to 1, by subtracting the minimum value and dividing by the range. False. B standardizes features by removing the mean and scaling to unit variance. This describes the function of standard scaler, not robust scaler. Standard scaler standardizes features by removing the mean and scaling to unit variance, standard deviation 1. False. C transforms features to have a median of 0 and a quantile range of 1, making it robust to outliers. This is the correct description of robust scaler. It centers the data around the median and scales it according to the quantile range, usually the interquartile range, IQR. This makes it resistant to outliers, as they have less influence on the scaling process. True. C transforms features to have a median of 0 and a quantile range of 1, making it robust to outliers. Robust scaler. A robust scaler that uses the median and interquartile range IQR to scale features. It is resistant to outliers because the median and IQR are less sensitive to extreme values than the mean and standard deviation. Robust scaler is useful in applications where outliers are common, such as financial data, image processing, and machine learning models that are sensitive to outliers. It can prevent these outliers from disproportionately affecting the scaling process and potentially harming model performance. Outliers. Data points that are significantly different from the rest of the data. They can be caused by errors in data collection, unusual events, or simply natural variations in the data. Outliers can cause problems in machine learning models, as they can influence the training process and lead to inaccurate predictions. Robust scaler helps mitigate this issue by making the scaling process more robust to these extreme values. Consider a dataset of house prices 100, 120, 130, 140, 150, 160, 170, 180, 190, 1000. The value 1000 is an outlier because it is significantly higher than the other prices. Robust scaler would scale the data based on the median and IQR, reducing the influence of the outlier. Quantiles. Values that divide a dataset into equal parts. The median is the 50th percentile, the 25th percentile is the value that separates the lowest 25 of data, and so on. Quantiles are used in various statistical analysis and data visualization tasks. Robust scaler utilizes quantiles, specifically the IQR, to scale features in a way that is resistant to outliers. In a dataset of exam scores, the 25th percentile might represent the score that separates the lowest 25 of students. The 75th percentile might represent the score that separates the top 25 of students. Data preprocessing. The process of preparing raw data for machine learning models. This includes steps like cleaning, transforming, and scaling data. Data preprocessing is essential for building accurate and reliable machine learning models. By preparing the data appropriately, we can ensure that the model can learn effectively from the data and make accurate predictions. Consider a dataset of customer purchase data. Before feeding this data to a machine learning model, we might perform data preprocessing steps such as 1. Cleaning missing values, example replacing missing purchase amounts with the average purchase amount. 2. Transforming categorical features into numerical features, example converting customer location into numerical codes. 3. Scaling numerical features, example scaling purchase amount to a range between 0 and 1. Feature scaling. Transforming the range of features to a common scale, often between 0 and 1 or a standardized distribution. This helps improve model performance and prevents features with larger scales from dominating the learning process. Feature scaling is a common data preprocessing technique used in various machine learning algorithms, such as linear regression, logistic regression, and support vector machines. It helps improve model performance by ensuring that all features contribute equally to the learning process. Suppose we have a dataset with 2 features, age ranging from 18 to 80 and income ranging from 10,000 to 1 million. Without scaling, income would have a much larger influence on the model's predictions than age. Feature scaling can help to address this imbalance by transforming the features to a common scale. Standard scalar. A scalar that centers features by subtracting the mean and then scales them to unit variance standard deviation 1. Standard scalar is commonly used in machine learning models where the assumption of normally distributed data is important, such as linear regression and logistic regression. Suppose we have a dataset with a feature representing the height of students, with a mean of 170 centimeters and a standard deviation of 10 centimeters. Applying standard scalar would transform the data so that the mean becomes 0 and the standard deviation becomes 1. Min-max scalar. A scalar that linearly transforms features to a specified range, typically between 0 and 1. Min-max scalar is useful when we need to scale features to a specific range, such as when using neural networks or algorithms that require features to be between 0 and 1. Suppose we have a dataset with a feature representing the price of products, ranging from 10 to 100. Applying min-max scalar with a range of 0 to 1 would transform the data so that the minimum price becomes 0 and the maximum price becomes 1. Machine learning models. Algorithms designed to learn patterns from data and make predictions. Machine learning models are used in a wide range of applications, such as image recognition, natural language processing, fraud detection, and personalized recommendations. A linear regression model can be used to predict the price of a house based on its size, location, and number of bedrooms. A logistic regression model can be used to predict whether a customer will click on an advertisement based on their demographics and browsing history. Linear regression. A model that finds a linear relationship between input features and a target variable. Linear regression is used in various applications, such as predicting stock prices, estimating housing prices, and forecasting sales. We can use linear regression to model the relationship between the number of hours studied and exam scores. The model might predict that for every hour studied, the exam score increases by 5 points. Logistic regression. A model that predicts the probability of a binary outcome, example yes/no, true/false based on input features. Logistic regression is used in various applications, such as predicting customer churn, detecting spam emails, and classifying images. We can use logistic regression to predict whether a customer will buy a product based on their demographics and browsing history. The model might predict that a customer with a specific age, income, and browsing behavior has a 70% chance of buying the product. Decision trees. Tree-based models that make decisions based on a series of rules derived from the data. Decision trees are used in various applications, such as medical diagnosis, credit risk assessment, and customer segmentation. A decision tree can be used to predict whether a loan application will be approved based on the applicant's income, credit score, and loan amount. The tree might have rules like 1. If income is high and credit score is good, approve the loan. 2. If income is low and credit score is bad, reject the loan. 3. If income is moderate, check the loan amount. If it is low, approve the loan. Otherwise, reject the loan. Support vector machines (SVMs). Models that find the optimal hyperplane to separate data points into different classes. SVMs are used in various applications, such as image classification, text categorization, and object detection. Suppose we have a dataset of handwritten digits. We can use SVMs to find the optimal hyperplane to separate digits into different classes, example 0, 1, 2, etc. Which of the following is not a use case for applying spline transformer in a machine learning pipeline? The question asks to identify a scenario where spline transformer wouldn't be the appropriate choice for a machine learning pipeline. A. Enhancing feature interactions in polynomial regression models. Spline transformer is used for polynomial regression models, but it doesn't focus on reducing dimensionality. It is designed to model nonlinear relationships between features and the target variable by dividing the data into segments and fitting polynomial curves. It can help in capturing the interactions between features, as it can create a basis of spline functions that can represent nonlinear patterns in the data. B. Capturing nonlinear relationships between features and the target variable. Spline transformer is explicitly designed for capturing nonlinear relationships, as it fits piecewise polynomial curves to segments of the data. It helps represent these complex patterns with more flexibility than linear models. C. Reducing dimensionality of high-dimensional data. Spline transformers' primary goal is to improve model performance by capturing nonlinear patterns and enhancing feature interactions, not reducing dimensionality. Dimensionality reduction is typically addressed by techniques like principal component analysis (PCA), linear discriminant analysis (LDA), or feature selection methods. D. All of the above. While spline transformer excels at enhancing feature interactions and capturing nonlinear relationships, reducing dimensionality isn't its core function. Therefore, all of the above is incorrect. C. Reducing dimensionality of high-dimensional data. As mentioned in the explanation for choice C, this option is the only one that spline transformer doesn't excel at. It is not designed for dimension reduction. This transformer creates a basis of spline functions, enabling representation of nonlinear patterns in data. Spline transformer works by dividing the feature range into segments and fitting polynomial curves to each segment. This allows for a more flexible representation of the data, capturing nonlinear relationships that linear models struggle to capture. It is especially useful for capturing complex relationships, such as those found in time series data or data with nonlinear patterns. A regression model that uses polynomial terms to capture nonlinear relationships between features and the target variable. Polynomial regression is a powerful technique for capturing nonlinear relationships. It adds polynomial terms to the linear model, allowing the model to fit curves instead of just straight lines. Spline transformer can be used to complement polynomial regression by introducing smooth, piecewise polynomial functions that improve model flexibility and help capture complex patterns in the data. These relationships occur when the change in the target variable is not directly proportional to the change in the independent variable. Linear models assume a direct proportional relationship between variables. However, in real-world scenarios, relationships are often more complex. Spline transformer helps to capture these complex patterns by creating flexible curves that adapt to the data's specific shape. This allows for a more accurate representation of the relationship between variables, leading to improved model performance. When multiple features combined have a more significant impact on the target variable than each feature individually. Feature interaction occurs when the combined effect of multiple features on the target variable is different from the sum of their individual effects. This means that the interaction between features is important to consider when building a predictive model. Spline transformer can capture these interactions by generating new features that represent combinations of existing features. This helps the model to learn more complex relationships between variables. Predicting house prices capture the nonlinear relationship between house size and price. Modeling customer churn identify nonlinear patterns in customer behavior that predict churn likelihood. Time series forecasting capture seasonal trends and cyclical patterns in time-dependent data. Spline transformer has numerous applications in machine learning. For example, in predicting house prices, spline transformer can be used to capture the nonlinear relationship between house size and price, leading to more accurate predictions. In customer churn prediction, it can help identify complex patterns in customer behavior that might indicate churn. In time series forecasting, it can help model seasonal trends and cyclical patterns in the data, improving the accuracy of predictions. From sklearn. Preprocessing import spline transformer. Transformer spline transformer degree 2, knots 5. Transformed data transformer. Fit transform data. Degree polynomial degree for each spline segment. Knots number of knots breakpoints to define the spline segments. The code snippet demonstrates how to use the spline transformer in Python. You import the transformer, initialize it with parameters like degree polynomial degree for each spline segment and knots number of knots, and then apply it to your data using fitTransform. The degree parameter controls the complexity of each spline segment. The knots parameter controls the number of segments and the flexibility of the resulting spline. Piecewise polynomial functions that smoothly interpolate between data points. Splines are piecewise polynomial functions that are used to represent curves. They are particularly useful for interpolating between data points, creating a smooth curve that passes through all the points. They are used in various fields, including computer graphics, engineering, and data analysis. Spline transformer utilizes splines to create a flexible representation of nonlinear patterns in data. Points where the polynomial segments connect, ensuring smoothness. Knots are points where the different polynomial segments of a spline connect. They are carefully chosen to ensure that the resulting spline is smooth and continuous. The number and placement of knots influence the flexibility of the spline. More knots allow for more complex curves, but can lead to overfitting if not carefully chosen. Set of functions that form a linear combination to represent the spline. Basis functions are a set of functions that can be combined linearly to create any function in a given function space. Spline transformer creates a basis of spline functions to represent nonlinear patterns in data. These basis functions are used to create a flexible representation of the data, capturing the nonlinear relationships between variables. The choice of basis functions is crucial for the performance of the transformer. You are building a machine learning model for predicting customer churn. Your dataset contains features like monthly charges and total charges with vastly different scales. Which sklearn preprocessing technique would you use to normalize these features to a standard distribution with zero mean and unit variance? A min-max scaler, B standard scaler, C robust scaler, D all of the above. Min-max scaler scales features to a range between 0 and 1. While it normalizes data, it does not necessarily result in a standard distribution with zero mean and unit variance. Incorrect. Standard scaler transforms features to have a mean of 0 and a standard deviation of 1, effectively normalizing the data to a standard distribution. This is often beneficial for algorithms that assume a standard normal distribution, improving performance, and preventing features with larger scales from dominating the learning process. Correct. Robust scaler scales features using a statistical method that is less sensitive to outliers. It does not necessarily normalize the data to a standard distribution with zero mean and unit variance. Incorrect. While all the options perform some form of scaling, only standard scaler achieves the specific goal of a standard distribution with zero mean and unit variance. Incorrect. B standard scaler. Feature scaling is the process of transforming features to a common scale. This is important for algorithms that are sensitive to feature scales, such as distance-based algorithms or gradient descent-based algorithms. In a customer churn prediction model, feature scaling is crucial to ensure that features like monthly charges and total charges are not unfairly influencing the model's predictions due to their different magnitudes. Data normalization refers to transforming features to a specific range, often between 0 and 1. This can improve the performance of some algorithms by reducing the influence of outliers and speeding up convergence. In a recommendation system, normalization could be applied to user ratings to prevent highly rated items from dominating the recommendations. Data standardization is a type of data normalization that transforms features to have a zero mean and unit variance. This is useful for algorithms that assume a standard normal distribution. In a fraud detection model, standardization can help ensure that features like transaction amounts are treated equally regardless of their original scale. The mean is a measure of central tendency that represents the average value of a set of numbers. In a sales forecasting model, the mean historical sales figures could be used to establish a baseline for future predictions. The standard deviation is a measure of dispersion that indicates how spread out the data is from the mean. In a quality control process, the standard deviation of product measurements could be used to identify potential deviations from acceptable tolerances. The variance is a measure of dispersion that represents the average squared distance from the mean. In a portfolio optimization model, the variance of investment returns could be used to assess the risk associated with different investment strategies. Machine learning models are algorithms that learn from data to make predictions or decisions. In a credit risk assessment model, a machine learning algorithm could be used to predict the probability of loan default based on borrower characteristics. The sklearn preprocessing module in Python provides various methods for data preprocessing, including feature scaling, normalization, and encoding. In a sentiment analysis model, the sklearn preprocessing module could be used to encode textual data into numerical representations that can be used by machine learning algorithms. The standard scalar class in sklearn preprocessing is used to standardize features by removing the mean and scaling to unit variance. In a medical diagnosis model, standard scalar could be applied to normalize medical measurements like blood pressure or heart rate, making the data more comparable across different patients. The fit transform method in sklearn preprocessing is used to fit the preprocessing parameters to the data and then transform the data according to those parameters. In a natural language processing model, fit transform could be used to create a vocabulary from a corpus of text and then convert the text into numerical representations based on that vocabulary. 50, 100, 150, 200, 1000, 2000, 3000, 4000, -1.224744871391589, -0.612372435695795, 0. 0.612372435695795, -1.224744871391589, -0.612372435695795, 0. 0.612372435695795. You are working on a machine learning project that involves predicting house prices based on features like location, size, and number of bedrooms. You notice that the location feature is categorical and contains many unique values. What is the best approach to handle this feature for your model? A1 hot encoding. B label encoding. C target encoding. D all of the above. 1 hot encoding is a popular technique for handling categorical features in machine learning. It creates a new binary column for each unique value in the categorical feature. For example, if the location feature has values city A, city B, and city C, then 1 hot encoding will create 3 new columns: location city A, location city B, and location city C. Each column will contain a 1 if the corresponding location is present and a 0 otherwise. True. 1 hot encoding is a popular technique for handling categorical features in machine learning. It creates a new binary column for each unique value in the categorical feature. For example, if the location feature has values city A, city B, and city C, then 1 hot encoding will create 3 new columns: location city A, location city B, and location city C. Each column will contain a 1 if the corresponding location is present and a 0 otherwise. Label encoding assigns a unique integer to each unique value in the categorical feature. This is a simple approach but can introduce an unintended ordinal relationship between categories, which may not be accurate. True. Label encoding assigns a unique integer to each unique value in the categorical feature. This is a simple approach but can introduce an unintended ordinal relationship between categories, which may not be accurate. Target encoding is a powerful technique that replaces each categorical value with the mean of the target variable for that value. It's useful for capturing the relationship between the categorical feature and the target variable, but requires careful handling to prevent overfitting. True. Target encoding is a powerful technique that replaces each categorical value with the mean of the target variable for that value. It's useful for capturing the relationship between the categorical feature and the target variable, but requires careful handling to prevent overfitting. All of the above methods are valid approaches for handling categorical features in machine learning. The choice of which method to use depends on the specific problem and the data being analyzed. True. Answer: D. All of the above. Categorical features are features that represent categories or groups. These features cannot be ordered or measured numerically. For example, location and color are categorical features. Categorical features are common in many machine learning data sets, such as in predicting customer churn, classifying images, and recommending products. In a dataset about houses, location would be a categorical feature because it represents different neighborhoods or cities. Feature engineering is the process of transforming raw data into features that can be used by machine learning models. This often involves creating new features from existing ones, selecting relevant features, and transforming features into a format suitable for the model. Feature engineering is crucial for improving the accuracy of machine learning models. It allows you to capture complex relationships in the data that might not be apparent from raw features. You can create a new feature called size of bedroom by dividing the size feature by the number of bedrooms feature. This new feature might be a better predictor of house prices than the original features. Encoding techniques are methods for converting categorical features into a numerical format that can be used by machine learning models. This is necessary because most machine learning algorithms require numerical input. Encoding techniques are used in a wide variety of machine learning applications, including classification, regression, and clustering. If you have a categorical feature called color with values red, blue, and green, you can use one-hot encoding to create three new features colored, color blue, and color green. Each feature will be a binary value 0 or 1, indicating the presence or absence of the corresponding color. One-hot encoding is a technique that creates a new binary column for each unique value in the categorical feature. The value of 1 is assigned to the corresponding column and 0 otherwise. This method preserves the categorical nature of the feature without introducing any ordinal relationship between the categories. One-hot encoding is commonly used for categorical features that have a small number of unique values. It is a simple and effective method for representing categorical data in a way that can be understood by machine learning models. In a dataset about cars, color would be a categorical feature. If the unique colors are red, blue, and green, one-hot encoding would create three new features colored, color blue, and color green. A car with red color would have colored set to 1, while color blue and color green would be 0. Label encoding assigns a unique integer to each unique value in the categorical feature. This is a simpler approach compared to one-hot encoding, but it might introduce an unintended ordinal relationship between categories which might not be true. Label encoding is suitable when the categorical feature has a large number of unique values, as one hot encoding might create too many features. It is also useful when you want to preserve the order of the categories. In a dataset about customer satisfaction, feedback could be a categorical feature with values satisfied, neutral, and dissatisfied. Label encoding would assign satisfied to 0, neutral to 1, and dissatisfied to 2. However, this could be misleading as it implies dissatisfied is greater than satisfied, which might not be true. Target encoding replaces each categorical value with the mean of the target variable for that value. This method directly captures the relationship between the categorical feature and the target variable, making it useful for predictive models. Target encoding is an effective approach for handling categorical features with a large number of unique values. It provides a more informative representation of the categorical data than one-hot encoding or label encoding. It is especially useful when the categorical feature has a strong relationship with the target variable. In a dataset about house prices, location could be a categorical feature. Target encoding would replace each location with the average house price in that location. This allows the machine learning model to directly learn the relationship between location and price. Overfitting occurs when a machine learning model learns the training data too well, including the noise and random fluctuations. As a result, the model performs well on the training data but poorly on unseen data. Overfitting is a common problem in machine learning. It can lead to models that are not generalizable to new data and make poor predictions in real-world scenarios. Imagine a model trying to predict whether a customer will buy a product. If the model overfits, it might learn that all customers who have purchased the product in the past are likely to buy it again. However, this might not be true for new customers, and the model will make inaccurate predictions. Regularization is a technique used to prevent overfitting in machine learning models. It adds a penalty term to the loss function, which discourages the model from learning complex relationships in the data that are not generalizable. Regularization is a widely used technique in machine learning. It is particularly important for models with a large number of features or when the data is noisy or limited. A common type of regularization is L2 regularization, which adds a penalty proportional to the square of the weights in the model. This encourages the model to have smaller weights, which reduces the complexity of the model and makes it less likely to overfit. Train-test split is a technique used to evaluate the performance of a machine learning model. The data is split into two sets, the training set and the testing set. The model is trained on the training set and then evaluated on the testing set. Train-test split is an essential step in machine learning model development. It allows you to assess how well the model generalizes to unseen data and avoid overfitting. Suppose you have a dataset of 1,000 examples. You could split the data into a training set of 800 examples and a testing set of 200 examples. The model would be trained on the 800 examples in the training set and then evaluated on the 200 examples in the testing set. Cross-validation is a technique used to evaluate the performance of a machine learning model more robustly than train-test split. It involves repeatedly splitting the data into training and testing sets and averaging the results across multiple splits. Cross-validation is a powerful tool for evaluating machine learning models. It provides a more accurate estimate of the model's performance on unseen data than train-test split. K-fold cross-validation is a common type of cross-validation. It involves splitting the data into k-folds. The model is trained on K1 folds and evaluated on the remaining fold. This process is repeated K times, and the results are averaged across all K folds. Model evaluation is the process of assessing the performance of a machine learning model. It involves measuring various metrics, such as accuracy, precision, recall, and F1 score, to determine how well the model performs on a specific task. Model evaluation is crucial for selecting the best model for a given task. It helps you to identify the model's strengths and weaknesses and make informed decisions about how to improve its performance. In a classification task, you might evaluate a model's performance using metrics such as accuracy, precision, and recall. Accuracy measures the overall percentage of correct predictions, precision measures the proportion of true positive predictions among all positive predictions, and recall measures the proportion of true positive predictions among all actual positive examples. Linear regression is a statistical method used to predict a continuous target variable based on one or more predictor variables. It assumes a linear relationship between the predictor variables and the target variable. Linear regression is a widely used technique in many fields, such as finance, economics, and healthcare. It can be used to predict stock prices, forecast sales, and analyze the relationship between different variables. Suppose you want to predict the price of a house based on its size. You can use linear regression to find a linear relationship between the size of the house and its price. The model will output a linear equation that can be used to predict the price of a house based on its size. What is the purpose of the sklearn.preprocessing.addDummy feature function? To scale features to a specific range. To remove features with low variance. To encode categorical features into numerical values. To add a constant feature to the dataset. To scale features to a specific range. False. Scaling features to a specific range is typically achieved using functions like sklearn.preprocessing.minmaxScaler or sklearn.preprocessing.standardScaler, not sklearn.preprocessing.addDummy feature. To remove features with low variance. False. Removing features with low variance is often done using sklearn.featureSelection.variance_threshold, not sklearn.preprocessing.addDummy feature. To encode categorical features into numerical values. False. Encoding categorical features into numerical values is handled by techniques like one-hot encoding or label encoding, not sklearn.preprocessing.addDummy feature. To add a constant feature to the dataset. True. The sklearn.preprocessing.addDummy feature function adds a constant feature, a column of ones, to the dataset, which serves as a bias term in linear models. To add a constant feature to the dataset. 1. Feature engineering. Transforming raw data into features that are more suitable for machine learning models. In a housing price prediction model, transforming the square footage feature by taking its logarithm can help improve the model's performance. 2. Dummy features. Constant features added to a dataset. In a linear regression model, adding a column of ones represents the intercept term, allowing the model to predict a non-zero value even when all other features are zero. 3. Sklearn.preprocessing.addDummy feature. Adds a constant feature to the dataset. Suppose you have a dataset with features x1, x2, and x3. Applying sklearn.preprocessing.addDummy feature to this dataset adds a new feature x0 with a value of 1 for all samples. 4 use cases. Intercept in linear regression. Bias term in neural networks. Regularization techniques. In linear regression, the intercept term, represented by the dummy feature, is used to adjust the line's position to better fit the data. In neural networks, the bias term helps the model learn a non-zero output even when all input features are zero. Some regularization techniques, like L1 and L2 regularization, penalize the model's parameters, including the bias term, to prevent overfitting. What does the sklearn.preprocessing.binarize function achieve in data preprocessing? Transforms data to a binary representation based on a threshold. Normalizes data to a range between 0 and 1. Scales data to a standard normal distribution mean 0, standard deviation 1. All of the above. Correct. The sklearn.preprocessing.binarize function converts data into a binary format 0 or 1 based on a threshold. Values above the threshold are assigned 1, and values below are assigned 0. The binarize function is a powerful tool for data preprocessing, especially when dealing with continuous data or categorical data that needs to be represented in a binary form. It converts all values above the specified threshold to 1 and all values below the threshold to 0. This can be beneficial for algorithms that work well with binary data or for reducing the complexity of the data for better performance. For example, consider a dataset with ages of people. We can use binarize to create a new feature indicating whether a person is above or below a certain age, example 30. Any age above 30 would be 1, and any age below 30 would be 0. This is useful for models that might perform better with binary input for age, instead of continuous values. The threshold value of 30 is set by the user based on the specific task requirements. Incorrect. Normalization scales data to a range between 0 and 1, but binarize converts data into a binary format 0 or 1 based on a threshold. Normalization is another essential preprocessing technique used to scale data to a common range. It is typically used for algorithms that are sensitive to the scale of the data, such as k-nearest neighbors, or algorithms that use distance calculations. It aims to reduce the influence of features with large scales on the model. For instance, consider a dataset with income values ranging from 10,000 to 1 million. Normalizing this data would scale the incomes to values between 0 and 1, reducing the impact of the large income values on the model and allowing it to focus on the relative differences between income levels. Incorrect. Standardization scales data to a standard normal distribution mean 0, standard deviation 1, while binarize converts data into a binary format 0 or 1 based on a threshold. Standardization is a preprocessing technique that scales data to a mean of 0 and a standard deviation of 1. It is often used for algorithms that assume a standard normal distribution for the data or for algorithms that are sensitive to the scale of the data. For example, suppose we have a dataset with height values ranging from 1.5 meters to 2.0 meters. Standardizing the height data would center the distribution around 0 mean and scale it so that the standard deviation becomes 1. This is useful for algorithms that require the data to have a standard normal distribution for optimal performance. Incorrect. Only A is correct, while B and C describe different preprocessing techniques. There are various preprocessing techniques used to prepare data for machine learning algorithms. Each technique serves a specific purpose. such as normalization, standardization, binarization, and more. Choosing the appropriate technique depends on the characteristics of the data and the requirements of the chosen machine learning model. A transforms data to a binary representation based on a threshold. What is the purpose of the sklearn.preprocessing.label binarize function in multi-class classification? To encode categorical features into numerical values. To convert a multi-class classification problem into multiple binary classification problems. To scale features to a specific range. To handle missing values in the dataset. To encode categorical features into numerical values. False. While encoding categorical features is important, label binarize specifically focuses on transforming multi-class labels into binary representations, not general categorical encoding. To convert a multi-class classification problem into multiple binary classification problems. True. This is the primary function of label binarize. It transforms a multi-class problem multiple categories into multiple binary classification problems, making it easier to apply algorithms like 1vs REST OVR. To scale features to a specific range. False. Feature scaling is a separate pre-processing step handled by functions like standard scaler or min-max scaler. Label binarize deals exclusively with transforming labels, not scaling features. To handle missing values in the dataset. False. Missing value handling is addressed using techniques like imputation or dropping rows. Label binarize doesn't directly deal with missing values. To convert a multi-class classification problem into multiple binary classification problems. Multi-class classification. A classification problem where the target variable can take on more than two distinct categories. For example, classifying images as cat, dog, or bird. Binary classification. A classification problem with only two possible outcomes. For example, classifying emails as spam or not spam. 1vs REST OVR. A multi-class classification strategy where you train a separate binary classifier for each class. Each classifier distinguishes one class from all other classes. For example, in a three-class problem, you would train three classifiers: cat versus dog bird, dog versus cat bird, and bird versus cat dog. Multi-label classification. A classification problem where an instance can belong to multiple classes simultaneously. For example, a movie could be labeled as action, comedy, and romance. 1vs1 OVO. Another multi-class classification strategy where you train a binary classifier for each pair of classes. For example, in a three-class problem, you would train three classifiers: cat versus dog, cat versus bird, and dog versus bird. Scikit-learn preprocessing. Scikit-learn provides a variety of pre-processing techniques for preparing data for machine learning. These include encoding categorical features, scaling features, handling missing values, etc. Label encoding. A technique for converting categorical features into numerical values using a mapping. For example, cat could be encoded as 0, dog as 1, and bird as 2. One-hot encoding. A technique for representing categorical features as binary vectors. Each category gets a corresponding column, and the value in that column is 1 if the instance belongs to that category and 0 otherwise. For example, cat could be represented as 1, 0, 0, dog as 0, 1, 0, and bird as 0, 0, 1. Classification algorithms. Algorithms designed to predict a categorical target variable. These include logistic regression, support vector machines (SVM), decision trees, random forest, naive Bayes, k-nearest neighbors (KNN), and many others. Logistic regression. A linear model used for binary and multi-class classification. It predicts the probability of an instance belonging to a specific class. Support vector machines (SVM). A powerful algorithm that finds the optimal hyperplane to separate data points of different classes. It is effective in high-dimensional spaces and works well with both linear and nonlinear data sets. Decision trees. Tree-like models that partition data based on features to create branches. Each branch leads to a prediction based on the features at that node. Random forest. An ensemble method that combines multiple decision trees to improve prediction accuracy. It reduces overfitting and improves generalization performance. Naive Bayes. A probabilistic algorithm based on Bayes' theorem. It assumes that features are independent, which may not always be true. Despite this, it performs well in many scenarios and is particularly effective for text classification. K-nearest neighbors (KNN). A non-parametric algorithm that classifies an instance based on its nearest neighbors in the feature space. It is a simple and versatile algorithm, but it can be computationally expensive for large data sets. Python. From sklearn. Preprocessing import label binarize. Cat, dog, cat, bird, dog. Binarized label binarize, classes cat, dog, bird. Print binarized. 1 0 0 0 1 0 1 0 0 0 0 1 0 1 0. The original labels are converted into a binary matrix where each row represents an instance, and each column corresponds to a class. A 1 indicates the instance belongs to that class, while a 0 indicates it doesn't. Which of the following statements is true about sklearn's min-max scaler? A min-max scaler scales features to a range between -1 and 1. B. Min-max scaler is particularly useful when dealing with features with vastly different scales. C. Min-max scaler can be used to address the issue of outliers in data. D. All of the above. Incorrect. Min-max scaler scales features to a range between 0 and 1. Correct. Min-max scaler scales features to a range between 0 and 1, making it suitable for features with different scales. Correct. Min-max scaler scales features to a range between 0 and 1, which can help to reduce the impact of outliers on model performance. Correct. Min-max scaler scales features to a range between 0 and 1, and is useful for features with different scales, and helps address outliers. D. All of the above. Feature scaling. Normalizing data to a common scale. Outliers. Data points that significantly deviate from the rest. Sklearn. Python's machine learning library. Image processing. Scaling pixel values for better model performance. Regression models. Scaling features before training regression models. Clustering. Scaling features for distance-based clustering algorithms. From sklearn. Preprocessing import min-max scalar. Data 10, 20, 5, 15, 25, 30. Scalar min-max scalar. Scaled data scalar. Fit transform data. Print scale data. The code demonstrates how to use the min-max scalar in Python. The first step is to import the min-max scalar class from the sklearn. Preprocessing module. Then, we create a list of data points. Next, we create an instance of the min-max scalar class. Finally, we use the fit transform method to scale the data and print the scaled data. The scaled data will be in the range of 0 and 1. Which sklearn preprocessing method scales features to a range between 0 and 1, where each feature has a unit norm. A standard scalar, B min-max scalar, C robust scalar, D normalizer, E all of the above. A standard scalar, font style font size 16 psquote. Standard scalar font. Standard scalar standardizes features by centering them around 0 and scaling them to unit variance. It doesn't scale features to a range between 0 and 1, and it doesn't ensure unit norm. False. B min-max scalar. Font style font size 16 psquote B. Min-max scalar font. Min-max scalar scales features to a range between 0 and 1, but it doesn't guarantee unit norm for each feature. False. C robust scalar. Font style font size 16 psquote C. Robust scalar font. Robust scalar scales features using a robust method, making it less sensitive to outliers. It doesn't scale features to a range between 0 and 1, and it doesn't ensure unit norm. False. D normalizer. Font style font size 16 psquote D. Normalizer font. Normalizer scales features to have unit norm, effectively rescaling them to lie within a unit circle or hypersphere. This is useful in scenarios where the magnitude of features is less important than their relative contributions. True. E all of the above. Font style font size 16 psquote E. All of the above font. Only normalizer scales features to have unit norm, so this option is incorrect. False. Font style font size 16 psquote D. Normalizer font. Font style font size 16 psquote normalizer scales features to have unit norm, effectively rescaling them to lie within a unit circle or hypersphere. This is useful in scenarios where the magnitude of features is less important than their relative contributions. Font. Font style font size 16 psquote normalizer can be used in text classification tasks to handle documents with varying lengths. By normalizing the feature vectors representing the documents, the model focuses more on the relative importance of words rather than the absolute number of words in a document. Font. Consider a text classification scenario where you're analyzing customer reviews. Some reviews are very short, while others are lengthy. Normalizing the feature vectors representing these reviews ensures that the model doesn't give undue weight to longer reviews just because they have more words. Instead, the model focuses on the relative presence of important words within each review. Font style quad font size 16 Scott from sklearn. Preprocessing import normalizer from sklearn. Datasets import loaderisld tyrese loaderisld text iris. Datald normalizer fits load normalize dex normalizer. Transforms load font. In this example, the code demonstrates how to use the normalizer class in scikit-learn. It loads the iris dataset, which contains measurements of flower characteristics like sepal length, sepal width, petal length, and petal width. The normalizer is initialized and then fit to the data. Finally, the transform method is used to normalize the data, resulting in normalized feature vectors with unit norm. Example data iris dataset. Sepal length, sepal width, petal width. 5.13.51.40.2 4.93.01.40.2 4.73.21.30.2 After normalization. Sepal length, sepal width, petal width 0.8340, 0.571, 0.229, 0.033, 0.847, 0.517, 0.240.034, 0.520.552, 0.224, 0.034. Font style quad font size 16 quote feature scaling normalization standardization unit norm scikit-learn preprocessing font. Feature scaling, the process of transforming features to a common scale, often done to improve the performance of machine learning algorithms. Normalization, a type of feature scaling that scales features to a range between 0 and 1. It is particularly useful when dealing with features that have different scales or units. Standardization, another type of feature scaling that centers features around 0 and scales them to unit variance. It is commonly used in algorithms that assume a standard normal distribution. Unit norm, the length of a vector, often used in machine learning to normalize feature vectors. Scikit-learn, a popular Python library for machine learning that includes a wide range of preprocessing tools, including normalizer. Preprocessing, the process of preparing data for use in machine learning algorithms. It can involve cleaning, transforming, and scaling data to improve accuracy and efficiency. What is the primary use case of sklearn. Preprocessing. Quantile transformer. A. To normalize data to a specific range, often between 0 and 1. B. To transform data to follow a specific distribution, such as a Gaussian distribution. C. To remove outliers from data. D. All of the above. Correct. Quantile transformer can indeed normalize data by mapping values to a fixed range. It works by dividing the data into quantiles and then assigning each data point a value based on its quantile, effectively compressing the data into a smaller range. This makes it possible to scale features to a common range, such as 0 to 1, which is beneficial for algorithms that rely on distance calculations or are sensitive to feature scales. Normalization. Normalization, as explained in the block normalization, involves scaling data to a fixed range, often between 0 and 1. It helps in ensuring that all features contribute equally to modeling by preventing features with large scales from dominating the process. This is particularly crucial for distance-based machine learning algorithms like k-nearest neighbors, which rely on distance calculations for classification or regression. In neural networks, Normalization can prevent vanishing gradients and facilitate more efficient learning by ensuring inputs have a consistent range. Correct. Quantile transformer can also transform data to follow a specific distribution by mapping quantiles to the desired distribution's quantiles. For example, it can be used to make data approximately Gaussian, which can be beneficial for algorithms that assume a normal distribution, such as linear regression. Distribution transformation. Distribution transformation, as explained in the block distribution transformation, refers to altering the shape of a data distribution to match a desired distribution, often a Gaussian distribution. This can be particularly beneficial for linear models that assume a normal distribution, as it can improve their performance. Additionally, kernel methods like support vector machines (SVM) that utilize Gaussian kernels can benefit from data resembling a Gaussian distribution, enabling them to effectively perform classification or regression tasks. Correct. While quantile transformer doesn't directly remove outliers, it can effectively mitigate their impact on modeling. By transforming data based on quantiles, it compresses the data and reduces the influence of extreme values. This makes models more robust to outliers, preventing them from unduly affecting model training and predictions. Outliers. Outliers, as explained in the block outliers, are data points that deviate significantly from the overall pattern of a dataset. These extreme values can negatively impact data quality and model performance. It is often necessary to identify and address outliers, either by removing them or adjusting their values, to improve data accuracy and model robustness. By utilizing techniques like quantile transformer, which can mitigate the impact of outliers, models can become more robust and provide more reliable predictions. Correct. Based on the explanations above, quantile transformer can perform all three functions: normalization, distribution transformation, and outlier handling. None. None. D. All of the above. What is the primary goal of using scikit-learn's robust scale function for data preprocessing? To normalize data to a specific range, typically between 0 and 1. To remove the mean and scale the data to unit variance. To reduce the influence of outliers on the scaling process. All of the above. False. While robust scaling can result in data within a certain range, its primary focus is not on achieving a specific range like normalization 0 to 1. Normalization. False. This describes the process of standardization, not robust scaling. Robust scaling is more resistant to outliers, whereas standardization is not. Standardization. True. Robust scaling's main purpose is to minimize the impact of outliers. It uses robust statistics like percentiles to achieve this. Robust scaling. True. Robust scaling achieves all of these goals: normalization, standardization, and outlier mitigation. It uses robust statistics to address outliers, which inherently results in normalization and standardization as well. Robust scaling. D. All of the above. A data preprocessing technique that scales features while minimizing the influence of outliers. It achieves this by using robust statistics like percentiles, example interquartile range. Machine learning algorithms sensitive to outliers, techniques like k-nearest neighbors (KNN), support vector machines (SVM), and linear regression can be significantly impacted by outliers. Robust scaling helps mitigate this by reducing the influence of extreme values. Datasets with high variance in datasets with features having vastly different scales, robust scaling helps standardize the features, preventing features with larger scales from dominating the model. Preprocessing for dimensionality reduction techniques like principal component analysis (PCA) often benefit from standardized data. Robust scaling can help prepare data for PCA when outliers are present. Python. From sklearn. Preprocessing import robust scale. Import numpy as np. Data np.array 1, 2, 3, 4, 5, 6, 7, 8, 9, 100, 101, 102. Scaled data. Robust scale data. Print scale data. Rescales features to a specific range, usually between 0 and 1. This helps ensure that features with different scales contribute equally to the model. Neural networks. Many neural network activation functions like sigmoid work best with inputs in a specific range, often between 0 and 1. Distance-based algorithms. Algorithms like KNN and clustering rely on distance calculations. Normalization helps ensure that features with larger scales don't dominate the distance calculations. Python. From sklearn. Preprocessing import min-max scaler. Import numpy as np. Data np.array 1, 2, 3, 4, 5, 6, 7, 8, 9. Scalar min-max scalar. Scaled data scalar. Fit transform data. Print scale data. Centers features around 0 and scales them to unit variance. This is often used for algorithms that assume features are normally distributed. Linear regression. Standardizing data can improve the performance of linear regression by preventing features with larger scales from dominating the model. Principal component analysis (PCA). PCA often works better with standardized data, as it relies on the covariance matrix, which is sensitive to feature scaling. Support vector machines (SVM). SVM models can benefit from standardized data, particularly when using kernels that are sensitive to feature scales. Python. From sklearn. Preprocessing import standard scalar. Import numpy as np. Data np.array 1, 2, 3, 4, 5, 6, 7, 8, 9. Scalar. Standard scalar. Scaled data scalar. Fit transform data. Print scale data. Which of the following statements are true about the sklearn. Preprocessing scale function? I. It centers the data by subtracting the mean. 2. It scales the data to unit variance. 3. It is useful for improving the performance of machine learning algorithms that are sensitive to feature scaling. Select the most accurate answer. A. Only I is true. B. Only 2 is true. C. Only I and 2 are true. D. All of the above are true. Incorrect. The statement is only partially true. While sklearn. Preprocessing scale centers the data by subtracting the mean, it also scales the data to unit variance. Font style quad font size 14 psquotlp.ltbgt. Only I is true. Incorrect. The statement is only partially true. While sklearn. Preprocessing scale scales the data to unit variance, it also centers the data by subtracting the mean. Font style quad font size 14 psquotlp.ltbgt. Only 2 is true. Incorrect. Both statements are true. Sklearn.preprocessing.scale centers the data by subtracting the mean and scales it to unit variance. The third statement is also true, making this option incorrect. Font style quote font size 14 c.ltbgt only I and 2 are true. Correct. The sklearn.preprocessing.scale function centers the data by subtracting the mean and scales it to unit variance. This is a standard practice for improving the performance of machine learning algorithms that are sensitive to feature scaling. Font style quote font size 14 d.ltbgt all of the above are true. D. All of the above are true. Feature scaling is a pre-processing technique used to transform features of a dataset to a common scale. This is essential for algorithms that are sensitive to the scale of features, as it prevents features with larger magnitudes from dominating the learning process. This improves the performance and convergence of the model. Font style quote font size 14 feature scaling refers to transforming the features of your dataset to a common scale. This is important for machine learning algorithms that are sensitive to feature scaling. Font. The sklearn.preprocessing.scale function is a standard scaler in scikit-learn that performs both mean centering and unit variance scaling. It centers the data by subtracting the mean and scales it to unit variance, effectively making all features have a mean of 0 and a standard deviation of 1. Font style quote font size 14 the sklearn.preprocessing.scale function is a standard scaler in scikit-learn that centers the data by subtracting the mean and scales it to unit variance. Font. Mean centering is a technique used to shift the data so that the mean of each feature becomes 0. This is achieved by subtracting the mean from each data point in the feature. Mean centering helps to improve the performance of algorithms that are sensitive to the location of data points, such as linear regression. None. Unit variance scaling is a technique used to scale the data so that the variance of each feature becomes 1. This is achieved by dividing each data point in the feature by the standard deviation of that feature. Unit variance scaling helps to improve the performance of algorithms that are sensitive to the spread of data points, such as k-nearest neighbors. None. Linear regression models can be sensitive to the scale of features, especially when features have widely different ranges. Scaling features to a similar range can improve the accuracy and convergence of the model. By using sklearn.preprocessing.scale, you can ensure that the coefficients of features with different scales are treated equally during the learning process. Font style quote font size 14 algorithms such as linear regression, k-nearest neighbors, support vector machines, and neural networks can benefit from feature scaling. Scaling helps to prevent features with larger magnitudes from dominating the learning process and allows these algorithms to converge faster and more accurately. Font. K-nearest neighbors KNN algorithm relies on distance calculations between data points. If features have significantly different scales, the distance metric will be dominated by features with larger ranges. Scaling features to a similar range ensures that all features contribute equally to the distance calculation, resulting in more accurate predictions. Font style quote font size 14 algorithms such as linear regression, k-nearest neighbors, support vector machines, and neural networks can benefit from feature scaling. Scaling helps to prevent features with larger magnitudes from dominating the learning process and allows these algorithms to converge faster and more accurately. Font. Support vector machines (SVM) are also sensitive to feature scaling. Scaling helps to prevent features with larger magnitudes from dominating the decision boundary, leading to more accurate classifications. Scaling also helps to improve the performance of SVM algorithms, especially when dealing with high-dimensional data. Font style quote font size 14 quote algorithms such as linear regression, k-nearest neighbors, support vector machines, and neural networks can benefit from feature scaling. Scaling helps to prevent features with larger magnitudes from dominating the learning process and allows these algorithms to converge faster and more accurately. Font. Neural networks are known to be sensitive to the scale of input features. Scaling features to a similar range helps to stabilize the learning process and prevents gradients from exploding or vanishing. This allows the neural network to learn more efficiently and achieve better performance. Font style quote font size 14 quote algorithms such as linear regression, k-nearest neighbors, support vector machines, and neural networks can benefit from feature scaling. Scaling helps to prevent features with larger magnitudes from dominating the learning process and allows these algorithms to converge faster and more accurately. Font. From sklearn. Preprocessing import scale. Data 1, 2, 3, 4, 5, 6. Scaled data. Print scale data. -1.22474487 -1.22474487 00 1.22474487 1.22474487. This code snippet demonstrates the usage of the sklearn. Preprocessing.scale function to center and scale a dataset. It takes a list of lists representing data points and returns the scaled version. Notice how the mean of each feature in the scaled output is 0 and the standard deviation is 1, confirming the function's behavior. What is the main purpose of sklearn. Preprocessing. Power transform. A. To normalize features to a specific range, typically between 0 and 1. B. To standardize features to have zero mean and unit variance. C. To transform features to have a more Gaussian-like distribution. D. To reduce the dimensionality of the data by eliminating redundant features. E. All of the above. False. While power transform can potentially impact the range of features, its primary purpose is not to normalize features to a specific range. Normalization is typically achieved using techniques like min-max scalar. False. Standardization is achieved using techniques like standard scalar. Power transform focuses on transforming distributions, not solely on standardizing mean and variance. True. This is the core functionality of power transform. It uses Yeo-Johnson and Box-Cox transformations to make feature distributions closer to a Gaussian shape, often beneficial for many machine learning algorithms that assume normality. False. Dimensionality reduction involves techniques like principal component analysis (PCA) or feature selection. Power transform focuses on feature transformation, not reduction. False. Since options A, B, and D are incorrect, this option is also incorrect. C. To transform features to have a more Gaussian-like distribution. Feature scaling is a data pre-processing technique used to transform features in a dataset to a common scale. This is often essential for machine learning algorithms that are sensitive to feature scales, such as distance-based algorithms example k-nearest neighbors or gradient-based algorithms example linear regression, logistic regression. In a customer churn prediction model, features like account balance and transaction frequency might have vastly different scales. Scaling these features ensures that the algorithm considers them equally. In a recommendation system, scaling user ratings on different products helps ensure that the algorithm doesn't prioritize products with higher rating scales over those with lower scales. A Gaussian distribution, also known as a normal distribution, is a bell-shaped probability distribution that is commonly encountered in many natural phenomena and statistical applications. Many machine learning algorithms perform better when data is approximately normally distributed. Linear regression models often assume that the residuals differences between predicted and actual values are normally distributed. If residuals are skewed, the model's accuracy can be affected. Many statistical hypothesis tests, like t-tests and ANOVA, rely on the assumption of normality for the data. The Yeo-Johnson transformation is a data transformation technique that can handle both positive and negative values, making it suitable for a wider range of data distributions compared to the Box-Cox transformation. In financial data sets where values can be both positive example stock prices and negative example losses, the Yeo-Johnson transformation can be used to normalize the distribution. The Box-Cox transformation is a data transformation technique used to transform non-normal data to a more normal distribution. It is applicable only to strictly positive values. In data sets with features like income or population size, where values are always positive, the Box-Cox transformation can be employed to ensure normality. The power transform function in scikit-learn provides a convenient way to apply either the Yeo-Johnson or Box-Cox transformation to features in a data set, based on the method parameter. It helps to ensure that features are more Gaussian-like, improving the performance of many machine learning algorithms. In a credit risk assessment model, transforming features like income and loan amount to have a more Gaussian distribution can improve the model's ability to distinguish between high-risk and low-risk borrowers. In a medical diagnosis model, transforming features like blood pressure and cholesterol levels can help to enhance the model's accuracy in detecting certain diseases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0.0, 0.52, 1.0, 1.41, 1.76, 2.07, 2.35, 2.61, 2.85, 3.07. Applying power transform to the sample data, which has a skewed distribution, yields a transformed dataset closer to a Gaussian shape. Which of the following statements are true about scikit-learn's power transformer? A. It transforms features to follow a Gaussian distribution. B. It is used for feature scaling. C. It can handle both positive and negative values. D. It utilizes a nonlinear transformation. This statement is correct. The power transformer aims to transform features to approximate a Gaussian normal distribution. This is achieved by applying Yeo-Johnson or Box-Cox transformations, depending on the data characteristics. The power transformer in scikit-learn performs a nonlinear transformation that aims to make the distribution of features more Gaussian-like. This statement is correct. While power transformer primarily focuses on distribution transformation, it indirectly contributes to feature scaling by bringing the features closer to a common scale. This is a side effect of making the distribution more Gaussian. The power transformer in scikit-learn performs a nonlinear transformation that aims to make the distribution of features more Gaussian-like. This is particularly useful for models that assume normally distributed data. This statement is correct. The power transformer handles both positive and negative values. It utilizes the Yeo-Johnson transformation for this purpose, which is applicable to data containing both positive and negative values. It achieves this by applying a Yeo-Johnson transformation or Box-Cox transformation, depending on the data's characteristics. This statement is correct. Power transformer employs a nonlinear transformation, either Yeo-Johnson or Box-Cox, to alter the feature distribution to a more Gaussian shape. This is fundamentally different from linear transformations used in methods like standardization. The power transformer in scikit-learn performs a nonlinear transformation that aims to make the distribution of features more Gaussian-like. All of the above. Linear regression. Power transformer can improve the linearity assumption of linear regression models by transforming skewed features to a more Gaussian distribution. Support vector machines (SVM). SVMs often benefit from data that is more Gaussian-like. Power transformer can prepare features for better SVM performance. Principal component analysis (PCA). Power transformer can improve the effectiveness of PCA by making the features more closely resemble a normal distribution. Feature scaling. Transforms features to a common scale, example 0 to 1, to improve model performance. Gaussian distribution. Bell-shaped distribution often assumed by many machine learning models. Yeo-Johnson transformation. A power transformation used by power transformer for positive and negative values. Box-Cox transformation. A power transformation used by power transformer for strictly positive values. 1, 2, 3, 4, 5, 10, 15, 20. Yeo-Johnson transformation. Let's say we have the data 1, 2, 3, 4, 5, 10, 15, 20, which is skewed to the right. Applying the Yeo-Johnson transformation, we can make the distribution more Gaussian-like. The transformation involves calculating a power parameter lambda and applying it to the data. The resulting transformed data will be closer to a normal distribution.